yeah, welcome everyone to this workshop, which is called Build Your First Audio Plugin with JUCE. It's hosted by the JUCE team, which consists of myself, Attila, Ruben, and Tom, who will be in the Discord channel answering your technical questions as I go through the workshop, and we'll be kind of swapping in and out for different sections. So yeah, if everyone could download the workshop materials, make sure they're in the Discord channel, this will go a lot smoother. So just a brief overview of what we're going to cover today. First of all, I'm going to talk about what exactly JUCE is, for those of you who don't know. Then we'll talk about the process of creating a JUCE project. We'll create our audio plugin project, which is contained within the workshop materials. And then we'll talk about broadly building audio plugins, making modifications to the code. We're going to build a very simple delay plugin in this workshop. And then there's a section at the end where we talk about testing your audio plugins that you've built. So broadly speaking, JUCE solves the problem of it's a cross-platform framework. So for example, you've got a computer and you want to write an app that just does something very simple, like draw a blue rectangle in the top left of the screen and a red rectangle next to it. So something in pseudocode might just look like this, where you're setting the color of some opaque graphics context and then giving it some coordinates to draw to the screen. And you've tested it, it works well on your desktop PC, so you would expect it to just run on your mobile phone. Well, you'd expect this to be the output, obviously scaled for the mobile phone screen, but that's not really the case, because although we're speaking at a high level, we're speaking C++, when we're writing our application, actually under the hood, this is speaking to the native operating system APIs, which are vastly different from one another. So on Windows, this will be the Win32 API, or more recently UWP. Android, you're talking to the native activity, which is going to be speaking Java. And then on Linux, you've got POSIX and X11 or Wayland as your windowing manager. And then on Apple platforms, you're talking AppKit and UIKit for the graphics side of things. So these APIs are a lot different to our initial pseudocode, and they're using platform-specific things. So this is how the same code that we had drawing our rectangle previously looks like in macOS. So you got this CG-rect struct, and then you need to tell it what color and give it a context, and then you can call fill rect. On Windows, it looks something like this. But you can see that the actual code that you need to write in order to do this is a lot different on the different operating systems. So to kind of illustrate this graphically and what problem we're trying to solve here, say you've written your application and it works well, and you've written it for Apple platforms. And so although this looks quite simple, it's actually hiding quite a lot of complexity. So under the hood here, your app is probably dealing with any number of these sort of lower level constructs. So it could be talking Midi, you might want audio, got things like file IO, networking, 2D, 3D graphics, GUI. And then if you go a level deeper, you've got the actual native frameworks on macOS. So you're speaking Core Midi, Core Audio, URLkit, Cocoa for the GUI. And then if you go a level deeper than that, you're actually talking OpenGL shader code, POSIX file system stuff, POSIX code. You might be talking to the USB and Bluetooth drivers, file IO, So it's actually vastly more complicated than a single piece. And then, yes, your app works perfectly fine on Apple platforms, but like we said before, it's not just going to work out of the box on all these other platforms. So you have to rewrite your application. So, you know, you're going to be writing wrappers around the APIs on Windows and Android and Linux to achieve the same functionality for your app. And JUCE is great in that it abstracts away a lot of these complexities. So we deal with all of the underlying native operating system API calls. We deal with all the complexity and the hassle of updates, deprecations, and so on. And when it comes to writing your application, you just have to write a single application using JUCE, and it will work nicely on all these platforms. So if we take our initial blue and red rectangle code, it looks something like this in JUCE. So you've got this graphics context, which is just called G. You're setting the color and just giving it some coordinates and drawing your blue and red rectangles. And as well as graphics, like we said before, your application might be talking audio, Midi, networking, might want to do some 3D graphics as well. So all of these are nicely handled by JUCE, and then JUCE just speaks to the underlying operating system APIs. And this is, an example for a desktop application, but you could quite easily replace the top of that with an audio plugin. And so you're speaking all of these different parts of your application, and that in turn will communicate via JUCE's audio processor API to the different plugin wrapper APIs. So you've got VST, AU, AAX, Unity plugins, RTAS, and then under that, you've obviously got all the different platforms that those run on as well. So JUCE will abstract away all of these complexities for you and makes it nice and easy to write a cross-platform app or plugin or mobile app, desktop app, without having to deal with all of these APIs. So now we've kind of talked and given a brief introduction to what JUCE is. We should start using it. So this workshop, we're going to be building an audio plugin from scratch. And by the end of the workshop, you'll have a nice, simple delay plugin that will run in your DAW. And hopefully the code should be nice and simple to extend and easy to understand. So you can sort of see what's going on and how you might build plugins in the future. So during the workshop, all the slides are numbered, and you have a copy of the slides in the workshop materials, so you can revisit any sections that maybe you want to go back over. You can refer back to them as you need. Like we said earlier, if you've got any technical questions or just any questions in general, then please post them in the workshop Discord channel, and we will be answering them during the workshop, and we'll also be around on Discord after the workshop to answer questions there if you've got any further questions. We'll take a couple of breaks during the session just because we realise it's quite a long time to be focused for 3 hours. So there'll be some kind of evenly spaced breaks where we'll take 5 or 10 minutes and you can grab a coffee or some food or something. And we'll make those clear as and when they occur. So we're going to be creating a plugin using JUCE. Like I said, it's going to be a fairly simple delay effect that you can run in your DAW, put it on a track, and it will give you a nice delay of the audio feed going through it. But there's quite a few steps to that to get over first. So the first step will be actually setting up the project using the producer. And then we'll jump into actually writing some C++ plugin code, writing a delay effect, We'll talk about compiling the different plugin formats and how you can build those, what gets built, the artifacts that are built, how you can load them. We'll load it up in the sort of simple plugin host that we've got going, which is also part of the workshop materials, so you can just quickly get it up and running. We're going to discuss some things like adding plugin parameters to your plugin and how those are mapped. We'll talk about creating a GUI for your plugin and how JUCE manages that, and how you can make some fairly complicated and interesting user interfaces with a minimal amount of code. And then finally, we will talk about testing the plugin, so verifying that it works correctly against the plugin APIs, that you're not doing anything silly. Things that won't be covered during the workshop because they're maybe a little more advanced or we just don't have time. We won't be covering things like more complex plugin audio configurations. So, for example, multibus or surround speaker arrangements. The plugin that we'll build will just be simple mono and stereo. We're not going to talk about mobile platforms. This is going to be just a desktop workshop. We won't be talking any performance optimizations, anything super in depth at least. So, we've got a nice delay effect, but it's not it's not hand tuned. We're not going to be doing any sort of hand tuned SIMD operations. We want to make it as easy to read as possible, and we won't talk about things like the plugin release process. So we're not going to go into installers, code signing, download managers, all of that. That's our can of worms. So yeah, we won't be diving into those. So the actual materials that you should all have downloaded and ready to go contain a few separate directories. So we've got the actual JUCE source in there. So there's a folder containing the whole of JUCE. We've got some binaries for the workshop. So there's a build of the producer and the test audio host for the various platforms, so macOS, Windows, and Linux. And then we've got numbered directories that contain all of the steps for the workshop. And there is a plugins directory, which is where you'll actually find the compiled plugins after they've been copied over. And there's finally this workspace directory, which we'll talk a bit about later, but that will be where you'll be building the plugin from. So at the moment, it contains the first step of the plugin. But if you need to reset at any point, you can just copy over the number directory into the workspace directory and start again. So the workshop materials contain a producer project that's already been generated. But the process for doing it is quite simple. If you just open the producer, you'll be presented with this screen for the first time where you can create a new project. So you'll be entering a name for the project, choosing some of the JUCE modules that you want to include, and then choosing the exporters and the platforms that you want to support. And then once you click the Create Project at the bottom, that will actually generate your producer project and the associated files that you can open up in your IDE. So we've done this step already. So if you go to the workshop materials and open the workspace directory, you'll see that it contains a producer project, also contains the source code and some IDE files that have been generated by the producer for the platforms. So that's macOS, There's a Makefile for Linux and Visual Studio projects for Windows. So this is the one of the workshop checkpoints. So you'll see at the very top of the title here, this is step 01, and that signals that we're using the contents of the 01 directory in the materials. And if you get lost or you just want to return to this step, you just need to delete the contents of the workspace folder and then just copy over the contents of the 01 folder, and you'll be back in a clean state. So yeah, we've already done this for the first step, so everyone should be starting from the same position. And so the objectives for this first step here, we'll be talking about some of the common project settings in the producer and what they do. We'll actually export the project and then open it in an IDE. And we will build the kind of empty auto-generated template project that we get given, load this up in the test host, and have a quick play. So if everyone can navigate to the producer directory of the workshop materials and open the producer for the platform that you're on. And then when that is open, open the producer project that's located in the workspace directory. So that's this file path, which is on the screen at the bottom there. So that's workspace, and then the simple delay.juicer file. If you open that with the producer, then you should be presented with this screen, which is a producer project. It's fairly simple. This is our simple delay project. So we'll just sort of go over some of the settings. I'm just going to try and increase my microphone gain. Is this a bit louder now? People were saying it was a bit quiet. Right, so when you open up the project, you'll be presented with this screen, and we'll just go over what some of these settings here on the left do. So if you click the settings cog in the top left, this will open the project settings, which contains all the settings kind of related broadly to the project. So you can set things like the version, line feed. This is where you can enable and disable the plugin formats, identifiers, all that sort of stuff. And then below that, we've got the File Explorer, which contains the source files of the project. This is where you can add and remove source files and manage them. And then below that is the module section. So JUCE is split into code modules, so where sort of each module broadly deals with a different part of the code base. So when we created our plugin template project, it added the necessary modules for building a plugin. So that's things like the audio basics, which is just your sort of basic audio I/O classes, devices, formats, and then the audio plugin client code, which is wrappers around the plugin APIs. And then you've got modules for core modules, some graphics modules, GUI modules, and so on. And then below that is the exporters settings page. So this is where you can manage the project files that you're going to be exporting to. And there are exporter specific settings in there as well. So this project has a Xcode exporter, then it has Visual Studio 2015, 17, and 19 exporters, and also a Linux Makefile. So then when you actually save the project, this save step will write out the project files for you, so you can then open it up in your IDE and you can start writing some code. So on macOS, for example, you would just hit the Xcode button, which is at the top here, and that step will save, generate the project files, and then we'll open the project in Xcode for you. So because we've already generated this project in the first step for you, we're not going to actually touch any of the settings. So we can leave it as is. And then just a note here that actually, if you are on Linux, I'm not sure how many people are, but if you are, then there's actually, because there's no standard IDE associated with Makefiles, there's no option to save and open in IDE. So you just have to actually save the project and then navigate to where the Makefile has been saved, and you can run make from the command line. So if I switch over here, what I've done is I've got the producer project open, and then if I close down Xcode, you can see that when I hit the Save and Open in IDE button here, it's going to save the project, and then also will open it up in Xcode for me. So the kind of broad project structure here is we've got our source directory. At the top level, we've got our delay project, and then in our source directory, we've got this plugin processor and plugin editor files, which relate to the JUCE audio processor and JUCE audio processor editor. So this editor is going to be dealing with the actual GUI for the project, and the processors will be writing our audio code. So now we've got this open in Xcode, we can build and run it. So in Xcode, there's a way to select the scheme that you're going to be running. So since we haven't set up the host quite yet, we're going to be running the standalone plugin format, which is a handy wrapper around just creating a desktop window for you and running the plugin in there. On Windows, this process is slightly different. So what you need to do is go to the solution, find the simple delay standalone plugin target, and if you right click on that, click set as startup project, then that will allow you to build it by hitting the local Windows debugger button at the top. On Linux, you need to navigate to the folder where the Makefile is located and run make, and then you can just open up the simple delay project. So if I demo this standalone project on Mac, I hit the run button here, Xcode's going to build it, and then once it's built, it will start running the application, and we'll get a window on the desktop that contains a very basic plugin that doesn't really do anything, but this will be our starting point. So we just wait for Xcode to build. And there we go. We now have a plugin, which you should all see on the screen now, just in front of the Xcode window. So at the moment, this doesn't do anything. It just has a really simple user interface, but we will be adding to this throughout the workshop. So to build the actual plugin files, not just the standalone, if we switch the scheme back to the all scheme and then hit Command B or product build, then this is going to build all the plugin formats for us. So it's build us a VST3 and an AE, as well as our standalone desktop plugin, and it will be placed in the plugins folder in the workshop materials. And then that's the plugin that you can load up in the test host or in your DAW of choice. And again, on Windows, the process for doing that is just hitting the build solution option or Control-Shift-B. And on Linux, if you just run make, that will build all of the plugin formats for you by default. So now we've got a plugin built. We can run it in test host. So we've got a really simple host app for testing our plugin, and that can be found in the workshop materials. So if you navigate to the test host folder in the workshop materials, and then open the binary for your platform, so whether it's macOS, Windows, or Linux, you'll be presented with this window. So at the top here, we've got some audio input sources. So there's a really simple cowbell sample, sine wave, saw wave, square wave, and noise. If you click on any of those buttons along the top, it will start inputting the audio. There's a gain fader and some level meters so you can see what's going on. And then this audio gets routed into the plugin, which you can add in the plugin section. And then there's a little oscilloscope underneath, so you can see sort of what the audio is doing. So to demo this, I'll just bring across the test host. So I need to build the actual plugin here. So I'm building the all target on Xcode. And then when that's done, that should copy over the plugin binary into the plugins subfolder of the workshop materials here. So now we can take our simple delay.vsd3, drag and drop it onto the test host here. And now if we click on this, this opens up our VST3 project, and we can see a desktop window. And you can, put audio into it, but it's not going to be doing anything useful at the moment because we've not actually written any audio processing code. It's just going to be doing the pass-through. But yeah, this is the process that we'll be using for the rest of the workshop, so it's good to get familiar with it. And yeah, so now we've sort of familiarized ourselves with the tools that we can use during the workshop. We know how to make a producer project, exactly how to export it and then build it in our IDE of choice on the platform that we're running on. We've also shown you how to load up the plugin in the test host, which we'll be using for the rest of the workshop.
Okay, so essentially we've already completed this workshop. You've already made a plugin with JUCE. It's just not a particularly interesting one, and we haven't really showed off anything that any of the capabilities that JUCE provides you. So from here on in, we're going to keep adding things to this plugin and showcasing some of the things you can do. This one will be the easiest. We're just going to go in and add a very simple gain reduction to the plugin. So show you how you can actually modify audio that's running through. If you are still struggling, then it might help if you copied the contents of the O2 directory into Workspace and then open the IDE project file directly from there rather than messing around with the producer. But if you have managed to keep up with this and you've got been able to load the plugin in the test host, then don't worry about it. So if you open up the project in your IDE, this is showing it in Xcode, we're going to work inside the plugin processor CPP file. Which is here. And the first thing you'll notice is that there's quite a lot going on in here. Almost all of this is filled out by the default plugin template in the producer, and it's setting things like, does your plugin handle Midi? Is it a Midi effect? What's the name? And various other kind of more general plugin configurations. But we don't need to worry about any of that. The actual audio processing is done in this function called process block. There's the implementation. Hopefully, most of it is fairly self-explanatory, but this is just like a skeleton for getting you looping over the audio, the incoming audio, and down here we're getting a breakpointer into it, which is where we can make some changes. So process block is called repeatedly by the host with a chunk of audio to process. The host typically have a setting that corresponds to the buffer size, usually a small power of 2, like 1024, 512, and this tells the plugin, or at least the host sends that number of samples in each buffer to the plugin. Something we will touch on again, but is useful for noting here, is that process block will be called on the audio thread, and the audio thread is not the same as that used for rendering graphics to your screen, handling mouse events, most file, I/O, and other things like that. And you should try as hard as you can not to mix the two. You'll notice that the first parameter in the process block function is this thing called a JUCE audio buffer. And it's this that holds the incoming audio data. Specifically, it's a class containing non-interleaved channels of audio data, where non-interleaved means that we have separate channels of contiguous audio data. So if you say, get me the data for channel 1, this will then be a series of floats where the value of the float ranges between -1 and 1. This gives you the amplitude of the audio. If you plotted it, this would literally be the waveform of the audio coming in. We're passed a reference to an audio buffer, which means that we can modify it, and any modifications to the audio is then passed on into the rest of the signal processing chain. If we change samples in this audio buffer, that's how we're going to affect the audio passing through this. That's exactly what we're going to do. We're going to zoom in at the bottom of this process block where we're getting a write pointer into our buffer, and we're going to modify it. I'm going to modify it in a very simple way. But I'm also going to copy and paste because I've found that typing in front of an audience, even a virtual audience, makes me almost incoherent. So what have we done here? So we can see coming into this function that we found out the total number of input channels, and we're looping over them. And we're saying for every channel of audio that we have, we're going to get a write pointer into the samples in that channel. And we're next going to find out how many samples of audio we have, and for every sample in the channel, we're going to multiply its value by 0.2, or equivalently divide it by 5, where the net effect of this is going to be that the amplitude of all our samples is reduced to 1/5 of what it was, and then that will reduce the volume. So let's see it in action. We're going to go up here and make sure we're going to build a plugin rather than a standalone. I'm going to build it. I just hit Command B, but if you go up to the top, you can go Product, Build, and it's a very similar workflow on Windows. And our project is built. So we'll open up our test host. our plugins is in the plugins directory. We'll drag this over to our test host. There's our plugin, still the same default GUI, but now anything running through it is much quieter than when we bypass it and we're not processing the audio. So we see we're having an effect on the audio that passes through. This is kind of the building, like the most important thing that plugins do is we modify the audio in the process block function. So that's how we modify audio, but you've noticed that it's not a particularly dynamic process. When we compiled it, we had a hard-coded value of 0.2, which can't be changed at runtime. So this is very fixed. The typical way of dealing with this in plugins is to add parameters. And plugin parameters are actually part of the plugin's interface. So when a host loads a parameter, it will query the parameter for various things. One of the first things of those is how many plugins do you have, what type are they, what are their names, and things like that. And because this is published as part of the plugin, this allows DAWs to do things like present generic UIs where everything is a slider. It enables you to do things like record automation. And you as a plugin author, it lets you kind of better encapsulate the logic of how you can interact with whatever audio processing algorithm you have sort of further down the chain. The other thing to mention is that parameters don't have to be visible to the host. If you mark a parameter as non-automatable, then you, as a plugin developer, can see it and can use it, but it won't be exposed to the host for automation and other things. The easiest way of doing this within JUCE is to use one of the audio processor parameter subclasses that we provide. These are a nice wrapper around parameters where the audio processor parameter classes provide methods for getting and setting parameter values and properties. And when you add these to your audio processor takes care of their lifetimes and interacting with them. And we've got a handful of basic types to get you started, where a float parameter is something that is very suitable for something like a slider. A bool would be a button. A choice would probably be a drop-down, and an int would be some kind of discrete setting. And we will add a parameter in the constructor. So again, this is in our audio processor CPP file. If you go up to the top, we're going to add a parameter. And we do this by calling a method on our audio processor, which is addParameter, and passing that one of these pre-built parameter subclasses that I mentioned on the previous slide. Where the parameters of the constructor of the parameter object are, this first one is an internal ID. So later on we'll show you how to refer to our parameters by these internal IDs. The next one is a public string to represent your parameter. So this would be displayed in a DAW, for example. And we have a minimum value, a maximum value, and a default value. And then once we've added our parameter to our audio processor, that then becomes part of the audio processor interface. So now we have our parameter, we need to be able to sort of get its value and feed our parameter's value into the audio processing that we're doing. And the steps we're going to take is this. There is another member function on our audio processor class, which is get parameters, which returns us a list of the parameters that we've registered. In this case, we've only told our audio processor about our gain parameter, so we only have one element. Take that, and that is our gain parameter. From there, we can ask it what its value is, store that, and then when we loop over the data in our audio buffer that we're modifying, we can, instead of multiplying by a fixed value of 0.2, we can now multiply the gain by, multiply the existing samples by the value of the parameter. Again, I will copy and paste that in and go through it again, just so anyone who is typing and keeping up has a chance. We went down into our process block. So previously, if we ignore these two lines, and just down here, we are multiplying by a fixed value of 0.2. Now, instead, we're going to multiply this float value called gain, where this floating point value we've obtained from our gain parameter by asking it what its value is. We've got the gain parameter by asking the audio processor to give us all of the parameters that it knows about, where we take the first element, because we know we've only got a single gain parameter. Now, if we build this, again, I hit a shortcut, but you can go to product, build, or the equivalent in your IDE. We fire up our test host. We can drag a plugin over. And I've missed an important step. The other thing we're going to do is stick up an automatically generated user interface. So you notice there, I came to go and modify the value of the gain and was greeted with just with the default hello world GUI, which I couldn't really do much. One of the bits of machinery that JUCE provides is a thing called a generic audio processor editor. And when you create one of these, rather than the default, this one is a bit smarter. So it will look at the audio processor that you pass to it. It will work out what all the parameters you've registered are, and then if it's a float parameter, it will display a slider. If it's a Boolean parameter, it will display a button, and so forth. So it's just a very quick way of throwing together some usable GUI. So that is just below our process block. There's this function called createEditor, and instead of returning the editor that's defined in our plugin editor source files, we're going to return a new generic audio processor editor. Then build this. Fire up a test host. Load the plugin that we've just built. Then you can see our gain parameter. So now, with a gain of 1, get a full volume, turn the gain down. It's much quieter. So we're going to start adding a bit of complexity, and for this section and the following one, it's best to sort of review the code changes as we go through. First off, because adding a delay effect has a reasonable amount of code just to implement the delay algorithm, and this is a workshop on how to make a JUCE plugin, not how to implement a delay effect. And in the following section, it's because the code isn't particularly interesting to type in yourself. Like here, it's quite easy to see where you could change something like a single number and see that reflected in the GUI or how your plugin sounds. But there really isn't that opportunity in these sections coming up. I can see a question that is, how do I load the built plugin into the test host? Well, I'll just show you doing that again. So you go down here into the test host, you find the test host for your platform, fire it up, and if you have built your plugin correctly, then you will see this plugin appear in the plugins directory of the materials. And then you can simply drag that and drop it here. Click it, you can load it up and see it. Right. So yes, with the caveats that if you're going to keep up now, you're going to have to be a really speedy typer. Let's go ahead and look at the code that we're going to add, rather than trying to keep along. So we should briefly tell you what a different delay effect is, so you can just have a bit of understanding of what you're going to hear. Delays typically introduce echoes of incoming audio. So when we send some audio to this plugin, it's going to remember it, and we're going to combine we're going to take any new audio and combine it with previous audio what we've heard at the time D, in this case, that has been recursively attenuated. Every time a time D comes, you'd hear an echo from time D, but with time it's going to get quieter and quieter. A very simple delay is going to feature a fixed delay time, but we're going to add two new parameters. One that will determine how quickly these echoes will die away, and another one which is a dry-wet mix control, where a completely dry sound is only the input and a completely wet sound is only the echoes, and this will be a fade between those two situations. So the first step is to add those parameters, and this should be fairly unsurprising. We have this first line, which is the same as we had before, where we added our gain parameter, and we just add two more lines, this time with a feedback parameter, where the only difference is that it has a default, the extra parameters that we're adding happen to have the same values. We're going to change them both between 0 and 1, but they have different default values. So the default for the feedback starts on 0.35, and the default for the dry wet mix is going to be 0.5, which is an equal blend between the dry and the wet. To do the delay algorithm, we're going to have a bit of state. We're going to have to remember a bit in our audio processor, and this is a simple circular buffer of audio history, where the size of the circular buffer, so a circular buffer is you keep writing audio data into it. When you get to the end of the buffer, you go back to the start of the buffer and just overwrite whatever is there. So that's going to be our kind of echo length. And each time we go around, the audio data that's already in there is going to get quieter. So the size of the circular buffer is going to determine the fixed delay. And each call we get into process block, we're going to add that audio into the circular buffer. So here's our bit of state. We go this time into the header file rather than the CPP file, and we add a couple of member variables to our class. This is the delay buffer that's going to hold our samples. We need to keep track of the position within the delay buffer that where we're currently at. And this is something new. So before, when you're using JUCE, before any calls to process block, before you do any audio processing, you will always get a call to prepare to play. And this gives you the chance to configure your algorithm for the subsequent calls to process block. In this case, we're going to need the sample rate. It would also give you an indication of how many samples per block you're likely to get. But we don't need this for now. So I said a few slides before that our delay is going to feature a fixed delay length. In this case, it's 200 milliseconds. Now, if or at least if your plugin is dealing with audio that has a higher sample rate, then you have many more samples in 200 milliseconds. So we need to size our delay buffer appropriately. So with increasing sample rate, you can see that the size of our buffer also increases. And then once that's done, we can call, we don't call, the host will call process block, and we will be configured correctly. And this is the delay algorithm, and we'll zoom through it. So the first thing we do is we get our parameters, like we've done previously, where we now, rather than just a gain parameter, we also have a feedback and a mix parameter. And this seems fairly dissatisfying in that you need to know that parameter 0 is your gain and parameter 1 is your feedback, then you're right, and we'll come back to this. This is kind of the meat of the algorithm, I guess. The important things to note here is that previously our entire algorithm just looked like this bottom line, where we were multiplying the data in our audio buffer by a fixed gain. But now it's also composed of this multiplication and some operations of the dry sample mixed with the delay sample, where the delay sample is coming from this recursively attenuated buffer of all audio played through our algorithm. And then finally, we just iterate over our delay buffer by the number of samples that we've processed. So let's do that. I will take a shortcut. So I've just used kind of the checkpointing system and jumped to the contents of the 05 source directory. And you can see it's built. Open up our test host. Drag it in our plugin. Oh, what on earth is going on there? And you see we've got these extra parameters, and with a bit of luck, you see that we're able to modify these parameters in real time, and we actually have a plugin, if not very interesting, at least you can have a play with it. Maybe have some fun. So the final bit of this section is how we can tidy things up a bit. I mean, we've already touched on the fact that the parameter management leaves a bit to be desired, and we can tidy that up and also touch on serializing and deserializing your plugin state by using this object that is the audio processor value tree state. Again, like the previous section, this isn't particularly, it's less typing than the previous section, but this isn't particularly fun typing. It's stuff you need to know if you're going to create a plugin, but it's not particularly interesting or fun to change interactively. So the first problem with parameter management, the way we were previously doing it, is that there's this kind of unknown map, or at least you as the programmer need to know that your mix parameter is index 2 in the array of parameters you get back. You can probably handle this with 3 parameters, but there are plugins out in the wild that have tens of thousands of parameters. I mean, you can see why this scheme just isn't manageable in that case. So how do we use one of these? Well, we add a bit more state to our audio processor. We have an audio processor value tree state as a member variable, and we initialize it in the constructor. So the constructor looks mostly like it previously did. You can see we've got these 3 audio parameter floats, same IDs, same labels, same parameters. But rather than calling add parameter on our audio processor, we're passing this information to the constructor of the audio processor value tree state. This is the only other really interesting parameter. We're not using it here, but instead of a null pointer, you could pass a pointer to an undo manager, where the undo manager does what it sounds like. It will record all of the changes to any of your parameters and provide a mechanism where you can undo and redo those changes as you or your user wants. And this is a common piece of functionality in plugins. This is the mechanism where you can kind of hook into that. Now, rather than asking the audio processor class what parameters it's got and just getting a list, you can kind of index into this state using those private IDs that we had before. And now it's fairly easy to see how the parameters correspond to at least there's no more of having to know an index where you can use the actual ID to get the parameter that you want. The other thing that the audio processor value tree state does is makes it much easier to serialize and deserialize your plugin state. This might sound like nice to have rather than something that's fairly essential to all plugins, but when you're working with your plugin in your DAW, a user typically spends a while tweaking all the settings to get a sound that they really like. And when you hit save, your plugin needs to be able to save the state of your plugin so that when that session is reloaded, it knows how to configure itself to get back into exactly the same state as it was before that sounded nice. The 2 functions that do this on the audio processor class are get state information and set state information, both of which are called by the host when it wants to either save or retrieve your plugin state. And these both work on serializing to and deserializing from a block of memory managed by the host, not by you as a plugin author. The actual mechanics of doing this is fairly straightforward. When the host wants to save your plugin state, it will call get state information, and if you're using an audio processor value tree state, you can simply say state, create a copy of that state. In this case, we turn it into XML. If that is successful, we have a pointer to some XML, and we just call this helper method called copy XML to binary, where it takes the XML and dumps it into this destination data, which is the memory, a block of memory provided by the host. You don't have to go via XML. You can trivially go straight from your audio processor value tree state to a binary representation. This will be much smaller and faster, but unless this process is really slowing you down, the benefits of having a human readable format for your saved state easily outweighs, well, when you come to debug and you can actually look at what a session was doing, you'll be very glad that you decided to keep it in XML or some other human readable form. And restoring your plugin state works in a very similar way, just the reverse process. So there's another helper function called get XML from binary, which you then have your generate some XML, and then you can create a value tree from the XML and call state, replace state with this state that you've deserialized from this binary data. And we can do the same. We can build the plugin, load it in the test host. This time, if you tweak some parameters, right-click on the plugin name, click unload, and then when you reload, you'll see that all of those parameter values were where you left them. If you like to watch the world burn, you turned everything up to 1, then when you reload, you see that you're still in the same state. So please do that, load it up, have a play, and hopefully everyone will catch up.
And now that we have some audio processing, we are going to create a custom graphical user interface. And as a start, we are only going to use basic shapes and text. And the reason for this is that even though JUCE comes with lots of pre-built widgets, this is going to show you the fundamentals of how those widgets are built up. And in this way, you can create truly unique and unique looking user interfaces yourself. So I myself have copied everything from the directory 06 into the workspace and opened it in Xcode. And I'm going to select the standalone plugin as a target, because when you want to iterate quickly, doing changes on the graphical user interface and just want to make sure that it looks right, it's actually quite handy if you don't need to load your plugin inside a host all the time. So I'm just going to build and execute the standalone. And if you have used the code in the folder 06, then we are going to pick it up exactly where we left it off before the break. And that should have gone easier. Okay, so Zoom is now having play with us. So what are the chances that it's going to work out all right now? Okay, interestingly, right now it's working and we can see the generic audio processor editor. And this is where we are going to pick it up. So we are going to start with basic shapes and text. But first, we are going to turn off the generic audio processor editor. And we are going to go with the simple delay audio processor again. And the processor editor is created inside plugin processor. And I'm going to search for the create editor function. I am going to comment out the generic part and enable the simple part. And we are just going to take a quick look what it looks like. So basically we just have a hello world graphical user interface. And before we would modify it, let's just take a quick look at the code that is responsible for drawing this user interface. So whenever you are working with the basics, you are going to be modifying the contents of the paint function. This is where you can use basic shapes and text. And this way, you can build up a completely unique looking user interface. Now, you may notice that the paint function has a JUCE graphics parameter. I will refer to this as the graphics context. So rendering graphics is a stateful affair. Basically, all of the state or most of the state that we are going to be modifying is encapsulated in this G graphics context object. And some of the functions that we will be calling on this object are going to modify the state of this object such that they will affect subsequent calls. For example, when we call the setColor function with white and then the setFont function with 15, it's going to affect the next call to draw fitted text. And it's going to draw a white hello world text with a height of 15 points or pixels instead. I will talk a little bit about this size, the pixels. But there's one more thing I want to mention. So we are also calling this fill all function. And basically we are filling the entire space that's occupied by our editor with a solid color, which is a background color ID. So what you can see here is that we are not hard coding the color into this code, and instead we are calling this get look and feel function. So I just briefly mentioned that the JUCE framework has support for encapsulating most of your style information into look and feel objects. And that way you can separate the style information from the structure of your user interface. For example, color information, color choices can be placed into these look and feel objects. And by calling get look and feel, you can retrieve the currently active look and feel object, and you can make skinned or skinnable GUIs if you would like to. So this is what we are going to modify. And I would also like to mention something that has been said before. So when you have a plugin with some user interface, you are working with at least two threads. One of the threads, the audio thread, is responsible for calling the process block function, which we were previously modifying. And there is a separate thread from this, which is rendering the graphical user interface. And you should be mindful of this in general, because oftentimes we would want to modify the parameters from the user interactions that were carried out on the user interface and read these parameters on the audio thread. And this way you can actually create race conditions without even realizing. And that's one of the difficulties of developing audio plugins. However, we will now stick to using audio parameters and the previously introduced audio processor value tree state. And if you are using these JUCE applied classes, they will actually make sure that the parameters are written and read in thread-safe ways. So let's draw something new. You can look at the picture and see that we will write a little bit of code, which is going to fill the background with black color and draw a cyan rectangle on top of it. And I am going to cheat and copy code myself. So as I mentioned, when you want to work with the basics, you have to modify the paint function inside the plugin editor CPP. So this is the code for our hello world, and I'm just going to replace it with these three lines. So we are going to fill the entire rectangle of the user interface with the black color. We are going to set the graphics context to a cyan color so that the next function we issue, fillRect, is going to draw this cyan rectangle. And I'm going to run the example, and let's hope that we will see the image we have seen before. So that's all right. And basically, this just shows you that you can modify contents of the paint function, press run, and immediately have feedback about how your user interface looks like. So in the following couple of slides, we are going to introduce a lot of new code, and it's okay if you don't try to keep up and copy everything yourself. You can just follow the flow of the presentation, and later on during the break, you can experiment with creating your own user interface components. So we are going to draw something more advanced, and to help appreciate what this code is going to do, let's have a quick peek at what it's going to look like. So we are going to create this geometric pattern where we have this dark gray background, and on top of this, we are going to draw black rectangles from the top left to the bottom right. And I am going to copy the corresponding code into Xcode and explain it line by line. So again, I am going to replace everything inside the processor editor paint function. And let's just look what we are doing. We are filling the background with this grayish color, then modify the graphics context state to refer to this black color. Then we are going to call the getLocalBounds function, which is going to acquire a rectangle which is covered by our editor on the screen. So oftentimes when you want to lay graphical objects out, you will refer to the rectangle that is covered by the entirety of the editor, and this is what this getLocalBounds is going to do in this case. We are going to specify this number 60, which is how many rectangles we would like to draw. And we are going to acquire the bottom right corner of this background rectangle and divide it by the number of rectangles. So what we are going to do is that we are going to create this loop, and we are going to run it 60 times, draw a black rectangle, and then basically move the top left position by this offset. And if we do it exactly 60 times, we are going to march from the top left corner to the bottom right. And again, I just press run. And we can see this geometric pattern. You have to pay attention because it's a dark gray and black shapes. And next, again, I'm going to take a quick peek. So we are going to place this large ADC text with a horizontal gradient pattern on top of this geometric pattern. And again, I am going to copy some code. So again, here is our paint function, and I am not going to delete what we have previously written. I'm just going to paste it here. So this was the previous code responsible for creating this geometric background. And then these instructions will be executed afterwards. So we are going to draw this ADC text on top of that background. Again, we use the getLocalBounds function, which is going to give us the rectangle covered by the editor. And then oftentimes a very handy way of laying out elements is calling these remove from type functions, which basically allow us to slice up this rectangle that we have started from. When I call remove from left with these parameters, I'm basically slicing off the left 2/3 of the previously acquired rectangle. And then adding even more calls, we can keep slicing these rectangles that we have. So first we slice off the left 2/3, then we slice off the bottom half from that, and then we are going to slice off 10 pixels from each direction. So probably this is a good time to mention that these pixels are actually adaptive pixels, so they do not map directly onto 10 pixels on your physical screen. The idea behind them is that when you create your user interface, it should physically occupy the same space, whether you are using a high DPI or a low DPI monitor. And basically the JUCE framework is doing this scaling in the background with the help of the operating system. So by slicing these rectangles, we have specified where the text should be placed. Then we create a gradient object, which is going to fade from one color to another. And the direction of the fade is going to be from the top left to the top right. So that's basically going to be a horizontal gradient. We modify the graphics context. We set the gradient field to this previously specified object. We set the font to the entire height of the text area. So what we want is for this text to completely fill this rectangle from bottom to top. And then we call the draw fitted text function. So let's see what the result of that is. And now we have the user interface that we were hoping for. So this is only the background of our user interface. And we used basic shapes to create it. So this gives you the maximum amount of freedom in creating unique looking things. But now we will keep building up our user interface by adding components on top of this background. So JUCE has a lot of widgets built in, and they are all inheriting from the component class. And what's notable is that every user interface is basically a tree of components. It's a hierarchical system. And in this case, the root of this hierarchy, the root component, is the audio processor editor itself. So when you want to place widgets on top of the editor, you have to create new components and make them children of the root component. The parent components are responsible for laying these children out, and they can even pass mouse events and keyboard focus in between them. So it's possible to handle these events only in the component that is affected by them. So JUCE has a selection of common widgets, as I mentioned. This time we want to control a number of parameters, and for them we will be using slider widgets. So I'm just going to give you a quick heads up. There will be 3 steps to adding sliders to our user interface. The sliders have to live somewhere, so we are going to create 3 slider members to the plugin editor. We then have to configure these sliders and make them children of the audio processor editor. And finally, we have to lay them out in the resized function. So I'm going to walk you through these steps and explain them as I do the pasting. So first, we will create 3 sliders, and we will make them live in the plugin editor class. I am adding a gain slider, a feedback slider, and a mix slider member to the plugin editor. Now we have to configure them and make them children of the editor. So this configuration is going to happen in the constructor of the plugin editor. Because this construction is the place where you are basically creating your user interface programmatically. So what I'm doing in the first 3 lines is I am configuring these sliders and I'm setting styles. The gain slider is going to be a linear vertical slider, and the feedback and mix sliders are going to be rotary sliders. Then I'm going to iterate over all 3 sliders and specify their style. What this line means is that I would like to see the value that the slider is controlling in the bottom of the parameter of the slider. And basically this call, add and make visible, is responsible for making this slider a child component of the audio processor editor. And there is the 3rd step, which is laying the children out. And laying the children out happens in the audio processor editor's resized function. So I'm going to resized. And the way to remember it is, let's say you want to create flexible user interface. In that case, if the user interacts with the user interface window and changes its size, you have to place the components again, because you would have to reorient them or change their sizes. So basically, anytime a user changes your plugin window, this resized function is going to be called. So this is the place where you should lay out these sliders. Again, we call get local bounds. So we have the rectangle that our editor is covering. We specify a margin size of 20. And again, we start slicing these local bounds. We move from the right. So we are going to place the gain slider on the right third portion of the user interface. We are going to place some knobs in the top half. And these knobs are going to be the feedback slider and the mix slider. So when I say you have to lay out the child components, that actually happens in the set bounds call. So for the gain slider, the feedback slider, and the mix slider, we have to call the set bounds function. And previously we have computed the rectangular area that we would like these sliders to occupy. So after these changes, I'm going to run our program again. And you can see that now we have these three sliders on top of our plugin window. You can even see some numerical values beneath them. However, they are not yet controlling the plugin parameters because we haven't specified to what parameters they should belong to. And that is going to be the next step. So actually, this is the step which where I would like to remind you that there is going to be an interaction between the user interface thread and the audio processor thread. And in order to be free of any race conditions and not have to worry about it ourselves, we are going to use the audio processor value tree state attachment classes. And basically, we will create three attachment objects, three attachment members inside the plugin editor. And these attachment objects will take care of synchronizing the graphical state of these knobs and the parameter values read by the audio processing code. So again, I'm going to take these three attachments and place them inside the plugin editor class. Now it's actually important that these attachments come after the sliders because an attachment is going to refer to the slider that it's controlling. And it's important that as long as the attachment object exists, the corresponding slider object should also have a valid lifetime. And by placing the attachment after the slider, we can ensure that. So we have created these attachment members, but we haven't initialized them yet. And it's in the initialization code where we are actually creating a connection between the slider and the corresponding audio processor value tree state value. So I go to the audio processor editor constructor, and I'm going to initialize all three attachment classes. And this is where I have forgotten one thing. So I would like to access the audio processor value tree state inside the audio processor. However, that member is a private member. So in production code, you would do better encapsulation, but right now, for us to have a play with this, it's actually fine to make this value tree state a public member of the audio processor. And this way, we can actually control them from our editor. So let's see if this compiles. So what you can notice at this point is we can actually see that these parameters are bounded. So these values no longer go up to 10, but only to 1. And I'm going to even open them inside the plugin host. So I'm going to switch over to building, say, the VST3 plugin. And I'm going to open the plugin inside the test host to see if our custom GUI is actually controlling everything. So in the plugin, I'm going to open this one. And I will open the user interface. And I will change the gain. And it's quieter now. So this is probably the feedback parameter. And if I increase the feedback, I can hear a lot of echoes. So that shows that these sliders are actually controlling the parameters. So when you have reached this point, and you can do that by copying the contents of the folder 10, I believe, or no, actually, you need to go to the folder 09 and you can copy the contents of it over to Workspace, and you can have a play with this plugin yourself, and you might even change, say, the number of rectangles that we are drawing.
So I'm going to be talking a bit about testing your plugin. Why is that important? Well, sometimes your program might behave in unexpected ways, for better or for worse, and you'll need to find out why so you can fix the problem. So testing is about looking for issues and their causes so that you can avoid any problems you encounter and make your programs and your plugins more robust. That's the idea. So debugging, how can we track down problems? A debugger is a program that helps you to test other programs and to locate issues in them, hopefully giving you enough information to fix any problems that you find. It's very useful if your program is doing something unexpected and you want to find out why it's doing that thing. So on different platforms, you'll often have access to different debuggers. So on Linux, by default, normally GDB is installed, and you can normally also install LLDB. On macOS, the debugger included in Xcode is called LLDB, and on Windows, Visual Studio comes with the VS debugger. And all of these debuggers will have some common functionality, which will include things like pausing the program so that you can inspect its state. You'll also be able to show the functions below the current function on the stack. So if you pause the program inside a specific function, you can see the entire stack of functions that led you to that point. And that's useful for answering questions like, why is this function being called, or which other function is calling my function? Debuggers will also allow you to evaluate functions and display their results while the program is running. So these are maybe functions that aren't hard-coded into the program source, but you might want to find out what would happen if you ran a function at a specific point. Maybe that would help you to locate some issue. And finally, debuggers often allow you to add logging output without having to modify or rebuild the program. So if you want to trace a series of function calls inside your plugin, then debuggers can let you do that without having to rebuild the plugin, which can speed up your development workflow a bit. And the main way that you do all of these things inside your debugger is by using breakpoints. These are the primary debugging tool of most debuggers. And a breakpoint just pauses the program at a specific point. So that point might be something like a pair of a line number and a file name, or it might be the name of a specific function in your project, or it might be after any exception is thrown. It's just a point where the program is paused. And then while the program is paused, you can inspect its state and you can view the call stack and you can do all of these good things that I mentioned earlier. And that should hopefully help you to find the cause of any issues that you've encountered. So debugging a standalone plugin is quite easy, and you might have already done it, in fact, without realizing. So when you hit run from your IDE, if you're building in debug mode, then the IDE will normally launch that program under the debugger automatically. So unless you specifically select a release mode build in your IDE, the run button in your IDE will normally launch the debugger for you. Debugging plugins in a host is a bit more difficult. You need to, in this case, you need to run the debugger on the host program, which means that you need to tell the debugger which host to run, where to locate it, or which process to attach to. You can also attach a debugger to a process that's already running, which is useful if you started your program or your plugin without a debugger active, but then encountered a problem and want to work backwards to find out what might have caused that issue. You can sort of retroactively attach the debugger, which is also useful to know. So how can we debug our plugin in a host? So not just a standalone, but an actual plugin. It's fairly straightforward. So in Xcode, we need to go to this edit scheme option in the scheme dropdown. And then under executable, we need to click other. This will bring up a file chooser where we can select our host. So this could be any host, but for now, it's probably best to test it out with the test host. It should be pretty quick. And then just hit run. And now you should see that the test host is launched instead of the standalone or your plugin. So now inside the test host, you should be able to load your plugin as you have been doing already. But now if you click on the line numbers on the left-hand side of the editor, you should be able to add one of these sort of blue arrows. This is a breakpoint. And when you then click one of the buttons in the test host to play some audio, the program should pause and you should see a sort of green line here and some other debugging output. I'll just show you how it looks on Windows as well, and then I'll actually run through the steps on macOS. So on Windows, it's pretty similar. You need to make sure that the program or the thing that you want to test is set as the startup project. And this just means that it will definitely, it will always be rebuilt before testing, which is useful so that you know you're always testing the most recent version of the project. Once you've done that, you can go to Properties. This will open a Properties window. And then you need to select Debugging from the left-hand side. And then under the command, pick Browse. That will open a file browser where you can locate the test host or any other host, but we're using the test host for now. It should look like this once you've selected the program. And then you should be able to click OK and then hit Run. And again, in VS, the way we set a breakpoint is by clicking in this sort of gutter next to the line number display. And again, in the test host now, if you play some audio, once you've loaded your plugin, this breakpoint should be hit, and you should see some debugging output. So I'll do that on my system before discussing Linux, because the behavior on Linux is a little bit different. So can you all still see my screen, hopefully? I'm going to go to, so I've got the VST3 scheme selected here. I'm going to go to Edit Scheme. Under the executable, I'm going to click Other. I'm going to find our test host, which is here. And I'm going to hit Run. And that's open on my other display. Here we go. So we've got our test host. And then I'm going to drag our VST3 into the test host. I've set a breakpoint inside our process block. And now when I hit the button to play a sine tone, you can see that the program pauses on this line. And this is a useful opportunity to look at the state of our plugin. So we can see the position of our delay buffer, which is 0, as we'd expect, because we've just fired up our plugin. We could also look at the contents of our delay buffer, its size, that sort of thing. On the left here, we've got our call stack. So this shows that we've called some functions in our test host. They've gone through the VST3 wrapper here. They've called this function called process audio, which is another function in the VST3 wrapper, which does an awful lot of stuff that we don't need to worry about just now. But eventually it's calling process block. So we can sort of see how this function has come to be called. And what you might find is when running under a debugger, your program might crash. If it crashes, you should also see this sort of debugger state. So you should see a call stack and the state of your program. In a crashed program, it's very useful to be able to see the call state because you can, the call stack, because you can see the series of function calls that have led to the crash a lot of the time. So it's quite helpful. So hopefully some of you have been able to debug, to pause the program. I'm going to assume you have and go back to the slide. So let's talk about Linux. On Linux, you probably won't be working inside an IDE unless you might be using CLion, in which case that does have a debugger built in. But it's also possible to debug from the command line. So the way you would do that is you would change your working directory to this Linux Makefile build folder. You'd run make and ensure that you're building in debug mode. This is the default, but it doesn't hurt to be explicit. So this just ensures that you're building in debug mode. Then you would run GDB, passing in the path to your test host. You'd set a breakpoint. So B just means add a breakpoint, and then pass the name of the function where you want to break. And then run will launch the program. And at that point, you're able to load the plugin as normal, play some audio through it. And when you hit that button to play the audio, the program should pause in a similar way to Xcode or VS. However, the output you'll see will be a little bit different because you'll be running in a terminal. So in that case, your output might look something a bit like this. So you can see it's that we've hit breakpoint 1 on our process block function. And at this point, you'll be able to enter commands in order to view the output, view the state of your plugin. Actually listing all of the GDB commands is quite involved, probably beyond the scope of this, this workshop, but this is quite well documented online. So you can look up commonly used GDB commands, and that should be enough to get you started. All right. Talked about that. Okay. Out of process loading. Why is this important? So not all hosts run the plugins in the same process as the rest of the DAW. So some hosts might run the main project and the plugins separately in separate processes. And this has some benefits to you as a music producer. It means that if your plugin crashes, then your DAW will hopefully be able to save and exit gracefully, so you'll be able to keep all your work. You won't lose anything. But as a plugin developer, this makes life a little bit more difficult because it makes it trickier to launch the host under a debugger. Because ideally, our debugger should be attached to the process that loads the plugin, but this will be different to the main DAW process. And we can't launch the plugin hosting process ourselves because normally this needs to be launched in a specific way by the DAW. And we don't necessarily know what that sort of special magic invocation would look like. So the way to get around this is to launch the DAW ourselves and then to attach the debugger once the DAW has opened to the plugin process. And I think I should be able to demonstrate that very quickly now. Or actually, I think I might have, sorry, I'm losing track of the slides. Yes, I'll talk about how you would do that in different IDEs. So the DAWs that do this are Bitwig, Reaper, depending on how you've configured it. I think by default, everything runs in the same process, but if you've changed some of the default settings, then you might have to worry about this. Also, AUV3 plugins in Logic do this. So you need to, in Xcode, go to Debug and then attach to process. In Visual Studio, it's very similar, Debug, attach to process. In GDB, you can run attach and then the process ID. Okay, so let's show what that looks like. So I'm going to open a copy of Bitwig, which runs the processes in the plugins in a dedicated process. Here we go, I've launched it in demo mode. You can see it's opened up here. Then in Xcode, we can go to our debug menu, attach to process. Then we can see that we've got not only the Bitwig Studio, which is the main process, we've also got this engine AVX2. Okay. So if you were trying to debug an issue that only occurred in Bitwig, you would want to launch Bitwig, open your plugin, and then run attach to process to track down the issue. Hopefully that will make sense. Okay, let's talk about notarization on macOS. So new versions of macOS from 10.15 onwards require that software distributed outside of the App Store must be notarized by Apple. Notarization is a process that automatically scans and validates programs for security issues. Software distributed inside the App Store also has to pass a similar series of security checks. So although they don't have to be explicitly notarized, they do have to pass the same sort of security checks. And one of these, the prerequisites for the security checks is that the app must not allow debugging, which makes our life a little bit difficult as developers who want to debug plugins. However, there is a workaround. Debugging is disabled on a host by omitting a specific key, this com.apple.security.getTaskAllow key from the host entitlements. And entitlements, as we've covered a little bit earlier, are properties of an app that are specified during signing of the app. And they tell your operating system what sorts of things the app is allowed or isn't allowed to do. So this includes things like starting the camera, starting the microphone, opening a Bluetooth connection, or allowing debugging, which is what we're interested in. So in order to debug a host application from a third-party developer, if that host application has been notarized, then we need to add this entitlement ourselves, which means re-signing the app. So it sounds a bit scary, but luckily it's quite straightforward. And the steps are just here. So we can run this code sign command, and this will output all of the entitlements that are set on a particular app. So this is our notarized app here. That will put all of the entitlements into a file. So we can edit that file to add this line here, adding this com.apple.security.getTaskAllow key. At this point, we've sort of missed a step here. I'd recommend backing up the original copy of your host app, just because this is a destructive process. You are modifying the signing of the app. So it's probably good to keep a copy just in case something goes wrong. It shouldn't go wrong, best to be safe. And then, yeah, we can set the new entitlements with this new key by calling code sign force with all of these options and passing our new entitlements file. Cool, hopefully that'll make sense. So we've covered now a bit about debugging. And debuggers are sort of general purpose tools. You might use them to track down issues in any sort of program. So not just hosts, not just plugins, but anything. But sometimes it's nice to have sort of more specialized tools to track down issues in the kinds of programs that you're working on, like plugins. And these tools do exist to stress test plugins specifically. And the idea is that these tests, these tools might test your plugin in lots of different, potentially unusual configurations to ensure that your plugin remains stable no matter what the host or the user asks the plugin to do. So a way of thinking about this is that you might use a stress testing tool to find out whether your plugin is stable or whether it has any issues in certain scenarios. If you find that your plugin does encounter a problem in some situation, you could then, using the stress testing tool, if you find out that your plugin has an issue, you might then use a debugger to find out the exact cause of that issue. So it's a sort of two-stage thing. You start out with the stress test. If you find an issue, move to the debugger and sort of drill in to find exactly what the issue is. Just gonna have a drink. So AUVal is one of these sorts of tools. This ships with macOS. It's an actual component of the operating system. So all macOS machines have this. And it's used by the system to test audio unit plugins to ensure that they're valid and to stop the user from accidentally opening like a broken plugin. It's important to note that in order to load an audio unit plugin in Logic, it has to pass AUVal validation first. So if you don't see your plugin in Logic, it's probably because it failed AUVal. So you might need to run AUVal manually to find out exactly what went wrong. So you can test a specific plugin by running this command that's shown here, auval-v, and then an identifier. If you don't know the identifier for your plugin, don't worry. You can run auval-a to list all of the plugins that are known, all of the audio units that are known to the system. And this will print both the names and the identifiers side by side. So you can look down the list to find the name of your plugin and then work out the identifier from there. It's also possible to run AUVal under a debugger. So if AUVal fails for some reason, you can launch it under a debugger and configure your debugger to automatically pass this set of flags, the -v and your plugin's identifier, and that will allow you to take a closer look at what's going wrong. This is easier on Intel than on ARM, unfortunately. So on Intel machines, it's quite straightforward to debug AUVal. On ARM machines, to the best of my knowledge, the AUVal process doesn't allow debugging, but it's also protected by the system. So in order to debug on ARM, you need to disable system integrity protection. So my recommendation would be, if you do have an AUVal failure, try to debug it on Intel, ideally. If you do have a problem that only becomes evident on ARM, unfortunately, you may have to disable system integrity protection on your Mac temporarily, just while you debug, but do make sure to re-enable it afterwards. We don't have instructions on how to do that, but you should be able to find them fairly painlessly by Googling disable SIP. So that's a Mac-only tool. Now we're going to talk about a more general purpose cross-platform tool called PluginVal. And this is, as I said, a more general purpose tool. So as well as allowing you to validate audio unit plugins on macOS, it also allows you to validate other plugin formats such as VST, VST3 on all platforms that JUCE supports, so Linux and Windows as well as macOS. It's also open source, which means that you can see exactly how each test works, which is really useful when tracking down particular issues, because it means that you can see both the hosting side and the plugin side, and it just makes it a bit clearer what's going on. It also has a command line mode, and this is useful for automatically testing. So For example, if you've worked on your plugin for a while, you might have some automated steps that run on GitHub or some platform like that. So as part of your automated build, you might also do some automated testing, and you could use plugin val to check that your plugin works after each commit. And the plugin, the command line mode is also useful for running under a debugger. So much as you could run auval automatically from your debugger, you can also configure your debugger to launch plugin val as the debugger process and tell it which plugin to validate. And plugin val also has a GUI mode, which is useful for sort of more ad hoc testing. If you just want to test a bunch of plugins all in one go and see if any of them have issues, then you might find the GUI mode useful. So to run plugin val in command line mode, it's very straightforward. You tell it the strictness level that you want and which plugin to validate, and that's all there is to it, really. What do the strictness levels mean? Plugin val has lots and lots and lots of tests, and some of them are harder to get your plugin to pass successfully than others. So if you want to run the full suite of tests against your plugin, you should select the highest strictness level, which is 10. And I'd strongly recommend trying to get your plugin to pass this, especially if you're releasing a professional sort of paid-for product. Plugins that only pass at lower strictness levels will still probably be usable in lots of scenarios, but they might also encounter issues if your user does something a little unexpected, or if the host isn't sort of API compliant, doesn't implement the standard properly. So yeah, I'd recommend trying to get your plugin to pass at strictness level 10 if possible. And I'll give some examples of the kinds of tests that plugin val runs as well. So it does things like enabling different bus layouts on your plugin, such as mono, stereo, surround, enabling and disabling sidechains if your plugin supports them. It also tests your plugin at different combinations of block size and sample rate. It has tests that save and restore the plugin state, and that might also move parameters in between the save and restore to check that when you call restore again, the original parameter values are restored correctly. And it also has a test that moves all the parameters simultaneously and checks that the editor remains responsive, which is quite fun to watch, just all of the sliders moving around very, very quickly. And that just about covers testing for the time being. This is, of course, a gigantic topic, so there's a lot more that we could talk about, and if you have specific questions, we'll do our best to answer, but we only have limited time here today. So what are some options for improving your plugin in the future? You've already got a simple delay working, but it might be nice to add some additional features. So a good place to start would be with parameter change smoothing. What I mean by that is, at the moment, each of your parameters moves directly to its new value at the beginning of each process block call. So, for example, the gain parameter, if it's moved quickly, might change values very rapidly or immediately at the beginning of each process block call, and then sit at that value until the start of the next process block call, where it might jump. And these jumps sound quite unpleasant. They will manifest as pops or clicks. Some people call it zippering if the parameters sort of moved over a period of time. And it's not really a desirable sound most of the time. So to counteract this, you would normally sort of interpolate or smooth the parameter value over the block. So from the previous parameter value to the most recently received parameter value. Luckily, there is a class in JUCE that helps you to do this. It's called linear smoothed value. And this is just a smoother class. You can give it a current value and a value to smooth to, and it will smooth the change over a certain number of samples. And you can also change the smoothing duration, all of that good stuff. So that's probably a nice place to start. You might also want to investigate allowing the delay time to be changed. So at the moment, we've got a static delay, but you might want your delay to sync up with the tempo of your project, and you might want your project to change tempos at some point, or you might want to use your plugin in multiple projects with different tempos, that sort of thing. So if you wanted to add this sort of feature, you would need your delay buffer to change, or you'd need a large maximum delay buffer, and you'd also need the read position in that buffer to be changeable. Once you've got a dynamic delay time, you might want to take that a step further and add a fractional delay. And this just means that the read head can move smoothly between sample positions, so you can get a really, really smooth automated delay effect. And luckily, again, JUCE has a helper class that might help you if you want to add this feature to your plugin. It's called JUCE DSP delay line, and it's a ready-to-use fractional delay with variable delay time. And finally, we've already touched on this a bit, but you might want to implement a custom look and feel for your plugin. Most plugins have a distinctive look. You can sort of tell which manufacturer built it, what the plugin is sort of intended to do. But at the moment, our plugin that we built today has a very sort of JUCE look. We're using the JUCE sliders that look very much sort of like JUCE sliders. So you might want to investigate skinning those. Yep. So where do you go from here? We've got some links here. The first link is to the JUCE repository on GitHub. I'd recommend checking this out quite frequently. You might want to update the copy of JUCE on your machine, on your system, fairly frequently too. We often contribute bug fixes, new features to the JUCE repository. It's always getting better, or we like to think it is. So definitely try to keep up to date. If you want to learn more about JUCE, you could visit our tutorials page at juice.com/learn/tutorials. There's quite a lot of content there, which we hope you'll find useful. And finally, we've got a socials link here. And of course, we're going to be hanging around in Discord for the next little while. So if you have any questions immediately, we'll do our best to answer them. And I think we'll all be hopping back onto the video call for the next 15 minutes or so as well. So I hope that's been helpful. Yeah, we'll do our best to answer your questions now.
So there was a question on the Discord about the ARA protocol, and that is actually something that Attila is working on right now. And so we're hoping that the next major release of JUCE will have the ability to use that protocol. Not quite within your process block. It's a bit more complicated than that. Actually, maybe Attila, could you say a bit more about what that's likely to look like?
Yeah, so the ARA protocol is basically providing additional interfaces on top of what's already available in JUCE. So when you create an ARA-enabled plugin, you gain access to another interface through which you can gain almost an unlimited look into the project opened by the DAW. So if you want, you can read the entire audio timeline. If you want to read samples from the end of the timeline, you can do that. I just try to make up a fancy example. Like you could create a plugin which is going to reverse the sound, which is pretty much impossible if you are doing a real-time processor, where you are only seeing the plugin, only seeing the buffer that you are given. So it basically enables the plugin to be a part of the DAW, an integrated part of the DAW, a lot more than it is right now.
There's a question about debugging output. And yeah, if you want to add debugging output into your program without using a debugger, you might find JUCE's DBG debug macro useful. and this will just print its arguments, but only in a debug mode build, so it won't print anything in release mode. So it's quite useful for debugging. However, if you have a debugger available, you can configure a breakpoint to output some logging information too, and that might be a better way to go, because it means that you don't have to keep rebuilding your plugin if you want to add or remove debugging statements.
And the other thing about the debug macro is that it will probably write the output somewhere sensible. It is surprisingly hard to do this with cout, cair, or logging manually, particularly for things like Windows plugins or Windows Standalone, where the idea of logging to a console and getting the output actually in the console or debugger that you're looking at is just a bit strange when you first come across it. Do you recommend any next step resources you have found helpful for plugin development? Well, if you're going to be using JUCE, the JUCE forum and the JUCE tutorials. I mean, the tutorials will give you like a better overview of the kinds of things you can do with JUCE, particularly in like sort of ancillary functions like downloading samples or embedding binary resources and things like that. And the JUCE forum really is very friendly. Right, so the majority of the posts there are beginners asking questions, helping them like get off the ground. And like we endeavour to answer all the questions, but the community is so nice that they can typically respond faster than us. So that's wonderful. So yeah, if you're getting started and want a bit of help, then you'll be absolutely welcome. For network calls, don't do them on the UI thread because a lot of them you might have to sit there spinning. Well, I mean, if the server's not there and you say wait for 5 seconds for a reply, that means you're not going to be processing mouse events or doing any windows for that long. But JUCE provides some networking functions where that's all taken care of asynchronously for you. Use those. Question here is, if I want to encode to another sample rate, can I do it without killing the audio thread? Yes. JUCE has sample rate converters that you can use. That's very common. So a very common thing in audio processing is to upsample your incoming audio. So you get it at what looks like a higher sample rate, which solves problems like aliasing later on. That's probably a bit advanced to go on here, but yeah, no problem with sample rate conversion. It's totally standard.
If you're making a delay that is synced to the host tempo, is there some standard slowest tempo that DAWs use? No. So you could either take a guess at the longest delay buffer that you might need, so just allocate, I don't know, 10, 20 seconds of storage. Yeah, I mean, that's probably the route I'd suggest. You might also, you could allocate it in prepare to play, so that you can sort of take things like the host sample rate into account when allocating the buffer as well.
Would I recommend a beginner to start on C-line or better stick to VS? I'm not sure. Maybe a couple of years ago I would have said it would be better to stick to Visual Studio, but now with better CMake support in JUCE, I don't think it makes much difference anymore.
I think it's really a producer versus CMake question, right? So if you're comfortable doing all of your configuration in CMake, then yeah, go for it. If you'd rather have a sort of friendly GUI tool to configure your project, then yeah, stick to the producer. It should make things a little bit easier. That being said, I do think that the CMake module is fairly well documented, so it should be pretty easy to get up and running with.
Yes, another comment on is there a minimum tempo that DAWs use, is that there is such a wide variety of DAWs across all the platforms as to make no assumptions about what DAWs will do whatsoever. That's just a kind of an unfortunate fact of life of being a plugin developer. Any do's and don'ts for minimizing the amount of unnecessary processes? In terms of multi-processing, where you're running audio processing in parallel, or just processes that you don't need to do and could be skipped? Broadly speaking, processing audio in parallel safely is quite difficult. I guess my do is, if you can possibly get away with doing all of your actual audio processing, your process block is just a single thread, then do that. You can use other threads to prepare things to play beforehand that you then pass to that audio thread. But trying to do any kind of cooperative multi-threading on the samples that are arriving from your process block is extremely difficult. It can probably be done, but I wouldn't ever plan to end up needing to do that. Would you have to be concerned about the same thread-safe constraints with Midi plugins as well? Yes. Although it seems like Midi might be a separate thing. In lots of cases, there's quite a tight binding between the incoming samples and the Midi messages, and they're handled on the same sort of footing. So yes, any kind of, you should be careful with any kind of live streaming data that comes into your plugin, be it Midi or audio.
But to add to that, in a JUCE plugin, the Midi messages will come in a Midi buffer as an argument to process block. So literally alongside the audio buffer. And the process block function is always called on the audio thread, or almost always called on the audio thread. Mostly called on the audio thread, depending on whether you're offline rendering or not. So yeah, all the same thread-safe considerations that you would make for audio apply to Midi too.
Right then. Thank you for everyone for staying towards the end, and I hope we've been able to sort of start your journey with JUCE and come out of this with an audio plugin that you can kind of poke a bit, change a bit, and see things happening. We will hang around in Discord for a bit, so if you're still catching up and get to the end and still have a question, we'll be there to respond. But otherwise, yeah, goodbye, and thank you very much.